what we want to do is solve the system of differential equations using the method of Laplace transforms. So we want to solve this IVP. Okay, so the first thing that we want to do here is that we haven't seen Laplace transform questions in this form yet, which is matrix form. And it's hard to do this while keeping this in matrix form. So the easiest way to proceed here is to convert this back into a system of first order differential equations. So what we can do is we can set y to be equal to x1, x2, where y prime is equal to x1 prime, x2 prime. Okay, so if we do this and we plug in what we get for our equations, and we also have our initial values. And now we want to solve this using Laplace. We know that for Laplace transform, we have the transform of the first derivative should be equal to so if we were to apply this to both of these, what we would get is something like this. We would have and each of these terms on the right side translate pretty simply. So now what we have is a system of two equations in x1s and x2s. And we can plug in our initial values that we found up here to cancel this out a little bit more. This x10 becomes 1, and then this x20 becomes 0. So from these two, if you want to solve for x1s and then x2s, solve for these two in this form, we have or actually, just to make this a little bit easier, we can write s plus 5 x1s. And then similarly here, we have so from these two, we can simplify and solve to get values for x1 and x2. We have after doing a partial fraction decomposition, we get and we can do the same thing to find x2s to get so from these two, we can use this and take the inverse Laplace transform to go back to our x of t formulas, and we get and thus we have our solution for y. And now if we want to check this, we can just plug this into Wolfram Alpha or just any computing program, and to just make sure that our initial value matches up 1, 0, and then that our solution in y also matches our original differential equation. So instead of doing that by hand, I just plugged it in here. So we have Here x1t is 9/8 e to the negative 4t minus e to the 4t over 8. So the same thing we got here. And the same thing for x2t, which is 9/8 e to the negative 4t minus 9/8 e to the 4t. And I just set up yt to be a matrix consisting of x1 and x2. So first thing we want to check is that the matrix form of y0, which means the initial condition, matches our 1, 0, which we see it does. Okay, so the next thing we want to check is that the derivative of yt is equal to our original yt multiplied by this matrix. So if we take the derivative of yt, we get this as our solution. We have a negative 1/2 e to the negative 4t times 9 plus e to the 8t for the first component, and then the second component is negative 9/2 e to the negative 4t times 1 plus e to the 8t. So that's our first derivative of y. Well, if we multiply y times our matrix, we get the same solution here. Negative 1/2 e to the negative 4t times 9 plus e to the 8t. And the second component is negative 9/2 e to the negative 4t times 1 plus e to the 8t. So our solution is a valid solution for our IVP.